In this lecture, we will be deriving the condition of a double-lined ground fault on the terminals of an alternator. So consider an unloaded alternator whose neutral is grounded through an impedance Zn. Let a double line to ground fault occurs between phases B and C through a fault impedance Zf. Okay. So we have considered an unloaded alternator. Here IA, IB and IC are the currents flowing out of the alternator terminals, and as the alternator is unloaded, before the occurrence of fault, IA, IB and IC are 0. Okay. Now we are considering that there is a double-lined ground fault between phases B and C. So phases B and C gets shorted and it is then gets connected to the ground through a fault impedance Zf. So a double line to ground fault through a fault impedance Zf. So current flowing through the fault path towards the ground is the fault current IF. Current flowing towards the ground, that is the fault current IF. We have also marked the phase voltages VA, VB and VC. Now, by examining its diagram, we can write the various boundary conditions. Okay, and the boundary conditions are, so as the alternator is unloaded, the current flowing through phase A, IA will be 0. This phase is open. So we can write IA is equal to 0, which is the first boundary condition. Then, see, this is the fault current IF, and we can see that IF is the sum of phase current IB and IC. So IB and IC together flows through the fault impedance towards the ground. So IF is equal to IB plus IC. The fault current IF is equal to IB plus IC. Now we can see that phase B gets shorted to phase C. So there is a short circuit between phase B and C. So this point gets connected to this point. So voltage VB, voltage of this point VB will be same as the voltage of this point VC. So we can write the voltages VB is equal to VC. Phase voltage VB is equal to phase voltage VC, and it is equal to, so it is the voltage between this point and ground. VB is the voltage between this point and ground, terminal of phase B and ground. Similarly, VC is the voltage between terminal of phase C and the ground, and it will be same as IF into Zf. It is also the voltage between this point and ground, IF into Zf. So we can write VB is equal to VC, which is equal to IF into Zf. So these three are the boundary conditions required for solving a double line to ground fault. Now let us calculate the symmetrical components of phase A voltage. So we can write symmetrical components of voltage are VA0, VA1 and VA2. So it can be obtained from the matrix equation 1 1 1 1 A square 1 A square A into VA, VB and VC. VA, VB, VC. Here it is VC, but as VC is equal to VB, I am writing here VB instead of VC. Okay. So this is the equation for calculating the symmetrical components of voltage. From this matrix, we can write VA0 is equal to 1 into VA plus 1 into VB plus 1 into VB. That is VA plus, sorry, here there is a 1 by 3. Okay. In the matrix equation, there is a 1 by 3 here. So VA0 is equal to 1 by 3 into VA plus 1 into VB plus 1 into VB, that is 2 VB. So VA0 is 1 by 3 into VA plus 2 VB. Now let us calculate VA1. VA1 is equal to 1 by 3 into 1 into VA plus A into VB plus A square into VB. VA plus A into VB plus A square into VB. So we can take VB common. So this will become 1 by 3 into VA plus A square into VB. Okay. And what is A plus A square? We know that A is the complex operator 1 angle 120, and we have already seen this relation, that is 1 plus A square is equal to 0. So from this equation we can write A plus A square is equal to minus 1. So instead of A plus A square we can substitute minus 1 here. So this will become 1 by 3 into VA minus 1 instead of A plus A square. So this will become 1 by 3 into VA minus VB. So positive sequence of voltage VA1 is equal to 1 by 3 into VA minus VB. Now let us calculate VA2, and VA2 will be equal to 1 by 3 into 1 into VA plus A square into VB plus A into VB. So we can write VA2 is equal to 1 by 3 into VA plus A square VB plus A into VB. So from here also we can take VB common. So this will be 1 by 3 into VA plus A square plus A into VB. So we have derived, so we know what is the value of A square plus A, that is minus 1. So VA2 will be equal to 1 by 3 into VA minus VB. A square plus A is minus 1. So we got both VA1 and VA2 as 1 by 3 into VA minus VB. See, VA1 is also 1 by 3 into VA minus VB. So VA1 and VA2 are the same. So we got VA1 is equal to VA2. So this is an important relationship. So note down it. Then now let us calculate the phase components of current. The various phase currents IA, IB and IC. The phase currents are, the equation is IA, IB, IC is equal to the transformation matrix 1 1 1 1 A square A 1 A square into the sequence currents IA0, IA1, IA2. Okay. So now let us write the expression for each of the phase currents IA, IB and IC. So first let us write the equation for IA. IA will be equal to 1 into IA0 plus 1 into IA1 plus 1 into IA2. That is IA0 plus IA1 plus IA2. And in this diagram we are considering an unloaded alternator, and we know that current flowing through phase A is 0. We have already wrote that condition as our boundary condition, that is IA is equal to 0. So we can substitute it here. Then we can write IA0 plus IA1 plus IA2 is equal to 0. So from here we can write IA0 is equal to minus of IA1 plus IA2. So this relationship is also important. Mark this also. Now let us calculate the next phase current, that is IB. IB will be equal to 1 into IA0, that is IA0 plus A square into IA1 plus A into IA2. Okay. Now let us calculate the third current IC, that is 1 into IA0 plus A into IA1 plus A square into IA2. So IA0 plus A into IA1 plus A square into IA2. Okay. Now we have to calculate the fault current. We actually have to derive the expression for the fault current, and we know that in case of a double line to ground fault between phase B and C, the fault current IF is equal to IB plus IC. Okay, so let us write IB plus IC. IF is equal to IB plus IC is equal to. So this is IB and this is IC. So let us add these two expressions. So IA0 plus IA0, that is 2 times IA0 plus A square IA1 plus A into IA1, that is A square plus A into IA1. A square plus A into IA1. And the third term is A IA2 plus A square IA2, which is again A plus A square into IA2. Okay, now it is 2 IA0. We know that A square plus A is minus 1. So minus IA1. Again, A plus A square is minus 1. So minus IA2. This can be written as 2 times IA0, taking minus sign common outside. So this will be IA1 plus IA2. Okay. Now what is minus of IA1 plus IA2? So we have already got an expression, that is minus of IA1 plus IA2 is plus IA0. So instead of minus IA1 plus IA2, we can write plus IA0. So 2 IA0 plus IA0, this will be equal to 3 times IA0. So in case of a double line to ground fault, the fault current will be equal to 3 times the zero sequence current. So we need this expression in the upcoming parts. So IF is equal to 3 times IA0. So next we are going to calculate the phase voltages. So phase voltages are equation is VA, VB, VC. They are the phase voltages, and this is equal to the transformation matrix 1 1 1 1 A square A 1 A square into VA0, VA1 and VA2. So from this matrix equation we can write the expression for VA, VB and VC. Okay. So see here, VA will be equal to VA0 plus VA1 plus VA2. VB is equal to 1 into VA0 plus A square into VA1 plus A into VA2. Similarly, VC is VA0 plus A into VA1 plus A square into VA2. So let us write it. VA is equal to VA0 plus VA1 plus VA2. And we already got this relationship, that is VA1 is equal to VA2. So this will be VA0 plus 2 times VA1. Now VB. VB is equal to VA0 plus A square VA1 plus A into VA2. Again, VA1 is equal to VA2. So we can replace VA2 by VA1. Then this equation will become VA0 plus A square plus A into VA1. And A square plus A is minus 1. So this will be VA0 minus VA1. VB is equal to VA0 minus VA1. Now let us calculate VC. VC is equal to VA0 plus A into VA1 plus A square into VA2. Okay. Now VA2 can be replaced by VA1. Then this will become VA0 plus A square into VA1. A plus A square is again minus 1. So this will also be VA0 minus VA1. So we can see that the phase voltage VB is equal to phase voltage VC. So we already knew this condition, we have included this as the boundary condition, that is VB is equal to VC. Okay. Now, let us consider the boundary condition. So, we have one boundary condition, that is VB is equal to VC is equal to IF into ZF. So, let us consider VB is equal to IF into ZF. So, let us consider we have VB is equal to IF into ZF. Now, what is VB? VA0 minus VA1. VB is VA0 minus VA1. So, VA0 minus VA1 is equal to IF into ZF, and we got an expression for IF also, that is the fault current IF is equal to 3 times IA0. So, instead of IF, write 3 times IA0 into ZF. Okay. Now, we know VA0 and VA1. VA0 is equal to minus IA0 into Z0 minus VA1. VA1 is EA minus IA1 Z1. This is equal to 3 times IA0 into ZF. Okay. So, now taking IA0 Z0 to the right hand side, the equation will become minus EA minus IA1 Z1 is equal to 3 times IA0 into ZF plus IA0 Z0. Then we can take IA0 common outside. So, this will become IA0 into Z0 plus 3ZF. Okay. So, from here we will get an expression for IA0. IA0 will be equal to minus of EA minus IA1 Z1 divided by Z0 plus 3ZF. Okay. So, we got an expression for the zero sequence current IA0 in terms of the positive sequence current IA1. So, what is our fault current? We actually have to calculate the fault current, and fault current is equal to 3 times IA0. So, we got an expression for IA0, but it is in terms of IA1, and we don't know IA1 also. IA1 is also unknown. Okay. But we got an expression for IA0 in terms of IA1. Now, we had another condition, that is positive sequence voltage is equal to negative sequence voltage. VA1 is equal to VA2. So, let us consider that condition. We have VA1 is equal to VA2. Now, VA1 is EA minus IA1 Z1 and VA2 is minus IA2 Z2. So, we can write IA2 as IA2 is equal to minus of EA minus IA1 Z1 divided by Z2. So, we got an expression for the negative sequence current I2 also, but it is also in terms of IA1. Now, we have to get an expression for the positive sequence current IA1. So, we also have the current of phase A, IA is equal to 0. That is, IA0 plus IA1 plus IA2 is equal to 0. And from here we can write the positive sequence current IA1 is equal to minus of IA0 plus IA2, or minus IA0 minus IA2. It is written from this equation. IA0 plus IA1 plus IA2 is equal to 0. So, IA1 will be equal to minus IA0 minus IA2. Okay, let us write IA1. So, IA1 is equal to minus of IA0. We got IA0 as minus EA minus IA1 Z1 divided by, so we got IA0 as minus of EA minus IA1 Z1 divided by Z0 plus 3 ZF. So IA1 is minus of IA0. So it will become plus minus IA2. IA2 is minus EA minus IA1 Z1 divided by Z2. So minus of IA2 become plus. So this is the expression for IA1. Now let us simplify this equation. Okay. So right hand side. Left hand side is IA1. Right hand side can be written as EA divided by Z0 plus 3ZF. EA divided by Z0 plus 3ZF minus IA1 Z1 divided by Z0 plus 3ZF. Minus IA1 Z1 divided by Z0 plus 3ZF plus EA by Z2 plus minus IA1 Z1 divided by Z2. Now let us take all the terms containing IA1 to the left hand side and keep all the remaining terms on the right hand side itself. So on the right hand side we have IA1 and this term minus IA1 Z1 divided by Z0 plus 3ZF will come to the left hand side, and this term also minus IA1 Z1 divided by Z2 will also come to the left hand side. So there will be three terms containing IA1 and we will be taking IA1 as common outside. So here when IA1 is taken from IA1, it will be 1 plus this term when comes to the left hand side it will become plus, and when IA1 is taken as common, remaining is Z1 divided by Z0 plus 3ZF. Z1 divided by Z0 plus 3ZF plus taking IA1 from this term, it will become Z1 divided by Z2, and the right hand side is EA divided by Z0 plus 3ZF plus EA divided by Z2. Or we can take EA common outside, right hand side will be EA into 1 divided by Z0 plus 3ZF plus 1 divided by Z2. Okay. Now let us take the LCM on the left hand side as well as on the right hand side. Okay. So left hand side becomes IA1 into, on taking the LCM it will be 1 into Z0 plus 3ZF into Z2, that is Z0 plus 3ZF into Z2 plus Z1 into 1 into Z2, that is Z1 into Z2 plus Z1 into 1 into Z0 plus 3ZF. So Z1 into Z0 plus 3ZF divided by Z0 plus 3ZF into Z2. Okay, and on the right hand side it will be EA into Z2 plus Z0 plus 3ZF divided by Z2 into Z0 plus 3ZF. Okay. So now on examining the equation we can see that the denominators are same. So let us cancel it. Now the remaining equation is IA1 into Z0 plus 3ZF into Z2 plus, so see the second and third terms, Z1 is common in both these terms. So take Z1 common, then it will be Z1 into Z2 plus, when taking Z1 common from this term, it will be Z2 plus Z0 plus 3ZF. Z0 plus 3ZF. Okay, and the right hand side is EA into Z2 plus Z0 plus 3ZF. Okay, now we actually need an expression for IA1. So keep IA1 on the left hand side itself. So we got IA1 is equal to this term divided by this term. Okay, so we can write IA1 is equal to EA into Z2 plus z0 plus 3zf divided by this term. Okay, so from this term, take this term common outside. z0 plus 3zf into zf. Let us take this as common. So denominator become z0 plus 3zf into zf. Okay, into. So when the first term, when this is taken as common, the remaining will be sorry, there is a mistake. This is z0 plus 3zf into z2. So I have wrote it as zf. It is actually z2. Okay. Now we have IA1 is equal to this term divided by this term. IA1 will be equal to, for calculating IA1 we have to divide the right hand side by this term. So we have IA1 is equal to EA into Z2 plus Z0 plus 3ZF divided by this term. And from this term, take this common outside. Z2 plus Z0 plus 3ZF. Take this term common. So this will be Z2 plus Z0 plus 3ZF into what is left. So when taking this term common outside, this will be Z1 plus, when we are taking Z2 plus Z0 plus 3ZF from this term, it will become Z0 plus 3ZF into Z2 divided by Z2 plus Z0 plus 3ZF. Okay, so this will be the expression for IA1, and here these two terms can be cancelled, and the final expression for the positive sequence current IA1 is EA divided by Z1 plus Z0 plus 3ZF into Z2 divided by Z2 plus Z0 plus 3ZF. Okay, so we got the expression for positive sequence current IA1 in terms of all the known values, the known sequence impedances and the fault impedance ZF. Value of EA is also known. It is 1 angle 0. So we got the positive sequence current IA1. Now we know how to calculate the zero sequence current and negative sequence current from IA1. We already have derived the expression for IA0 and IA2 in terms of IA1. So after calculating IA1, calculate IA0 and IA2, and we have the fault current IF is equal to 3 times IA0. So after getting IA1, we can calculate IA0 and IA2, and then fault current IF will be equal to 3 times IA0. So IF is equal to 3 times IA0. So now let us draw the sequence diagram for this particular condition, a double line to ground fault. Okay, so for drawing the sequence diagram, we need some of the expressions that we have derived earlier. Okay, we got VA1 is equal to VA2. So these two voltages are equal. Terminal voltage across the positive sequence circuit and that across the negative sequence circuit are equal. That means these two are in parallel. The positive sequence network is in parallel with the negative sequence network. So first of all, let us draw that part. The positive sequence network in parallel with negative sequence. So positive sequence network is positive sequence impedance in series with a voltage source EA. Okay, now this and the negative sequence network are in parallel. Negative sequence network will have the negative sequence impedance only. So current flowing out of the positive sequence network is IA1, and that out of the negative sequence network is IA2. Terminal voltage of positive sequence network is VA1, and that of the negative sequence network is VA2. Okay, so we have completed that part. So from the equation VA1 is equal to VA2, we have drawn this much. Now let us see the equation for current IA1. Okay, see, we got IA1 as EA divided by Z1 plus Z0 plus 3ZF into Z2 divided by Z2 plus Z0 plus 3ZF. Okay, we know that a current is equal to voltage divided by impedance. So current IA1 is equal to total voltage divided by total impedance of the circuit through which IA1 is flowing. So the total impedance of the sequence network is this much. So let us examine this term. The denominator term denotes the total or equivalent impedance of the sequence network. So see, there is a term Z1 plus another term. So adding two impedances or two resistances means this one is in series with the second term. So these two are in series. Z1 is in series with this particular impedance. Now let us examine the second term, and in second term it is equivalent to R1 R2 divided by R1 plus R2. Okay, so let us consider this term as R1 and this is as R2. So it is R1 into R2 divided by R1 plus R2, which means the parallel combination of equivalent resistance of parallel combination of two resistances. Z2 into Z0 plus 3ZF divided by Z2 plus Z0 plus 3ZF. That means Z2 and Z0 plus 3ZF are in parallel. Z2 and Z0 plus 3ZF are in parallel. That is why their equivalent is taken as Z2 into Z0 plus 3ZF divided by Z2 plus Z0 plus 3ZF. So these two are in parallel. Z2 and Z0 plus 3ZF are in parallel. Now Z0 plus 3ZF. So that means Z0 and 3ZF are in series. That is why we are adding Z0 and 3ZF. So Z0 and 3ZF are in series, which is in parallel with Z2, and the entire combination is in series with Z1. Now let us draw the diagram. Z2 is in parallel with Z0 plus 3ZF. So let this be 3ZF. 3ZF and Z0 are in series. Okay, so let this be Z0. Z0 and this is Z3ZF. So this will become Z0 plus 3ZF, which is in parallel with Z2, and the entire combination is in series with Z1. So we will get the expression for IA1 from this sequence diagram. Okay, so we can see that expression for IA1 and this sequence diagram are comparable to each other. Okay, now so actually we don't have to by heart the equation for IA1. If we can remember this particular sequence diagram, then we can easily write the equation for IA1 from this diagram. Okay, IA1 is the total current flowing out of this source, and total current is equal to total voltage, that is EA, divided by equivalent impedance of this circuit, and that is Z0 plus 3ZF. These two are in series, which is in parallel with this one, and the entire impedance is in series with Z1. That is Z0 plus 3ZF into Z2 divided by Z2 plus Z0 plus 3ZF. It is the equivalent of this much of portion, and this entire section is in series with this one. So plus Z1. Okay, so we don't actually have to by heart the equation for IA1. We just have to remember this sequence network. Then we can easily write the equation for IA1 also. Now let us consider one special case also, that is a direct fault. Direct short circuit between phases B and C. Direct or solid or bolted fault. Okay, so in that case there will be a direct short circuit between phase B and C and to the ground. That is ZF will be equal to 0, and in that case we will get the positive sequence current IA1 as EA divided by Z1 plus Z0 into Z2 divided by Z0 plus Z2. Okay. So calculate IA1, then calculate IA0, and 3 times IA0 will give us the fault current IF.